Good evening, everyone. Uh, this is Group SWML4, and we are delighted to present your project titled A Multimodal Acoustic Electrical Feature Extraction Framework for Machine Learning-Based Partial Discharge Classification. Before we go deeper into our presentation, we are going to introduce ourselves by the names of Mabe Junior Humphrey.
I'm Cargo and Treasure.
I'm Ayan Mustafa Abdurrahman.
Thank you. Can you please move to the third slide? The core motivation is that partial discharge, or PD as call it, is an early warning sign of insulation failure in high voltage assets such as transformers, generators, and the switchgear. If PD is not detected early, of course, repeated stress accumulates, insulation degrades, and then this can finally result into equipment failure and power outages. So our work focuses on early, automated, and explainable PD diagnosis for predictive maintenance. Next slide, please. Yeah, from our related work, we learned that the traditional PD monitoring has a strong theory and instrumentation, but practical deployment still faces challenges in noisy environments, multimodal alignment, and robust localization. This informed our computational problem. Now, PD signals, as we all know, are high frequency, noisy, and feature redundant, with interference from real operating conditions. Therefore, the system must extract temporal and spectral information, and then also separate corona, internal, and surface classes, and localize the likely source region. Next slide, please. Our research questions were split by modality. For the acoustic dataset, we asked about structure consistency, waveform variation by channel and location, domain time, frequency patterns, and clustering behavior. Whereas for the electrical dataset, we asked about consistency, pulse shape uniqueness, phase resolved behavior, and whether statistical plus spectral features separate discharge types. Yeah, next slide, please. And then for our research contributions and outputs, we conducted, of course, the EDA on the acoustic and electric PD data sets to understand different signal behaviors and also the distribution patterns. Later on, we trained 12 models on both the acoustic and the electrical data sets with the aim to detect PD or maybe locate PD and classify PD. And then from the 12 models, we identified two well-training models that we actually later on further trained and then deployed to get results of them. Then for our research outputs, we cleaned what and structured the data sets that we had. And then we generated the 12 models that we actually trained from the acoustic and the electrical data sets. And then we we got two well-performing models, that is the GPC model. We trained it on the electrical data set to classify the PD, and then also the STGNN model trained on the acoustic data set. And then at the end of it all, we were able to generate or create a semi-supervised multimodal fusion model that actually detects and classifies PD. Can you move to the next slide, please? This slide tells us or talks furthermore on the system architecture. Now, this architecture shows our full reasoning stack from synchronized sensing to actionable output. At the top, we start with the sensor layer where we find the HFCT electrical sensing and microphone array acoustic sensing synchronized through FPGA timing. Now that synchronization is critical because a multimodal fusion only works if events are aligned with time. And then on the next row contains four parallel processing blocks. The neural layer captures non-linear representations from the data. The plus detection isolates discharge events from background activity. Feature extraction transforms raw signals into discriminative descriptors in time and frequency space. And then the probabilistic matching then aligns modality evidence and estimates how likely each candidate interpretation is. Now, these outputs feed into the causal layer where time of arrival logic and physics validation enforce consistency with real propagation behavior. This step prevents the model from accepting physically different combinations, which improves trust in noisy conditions. Then we move to the symbolic layer where phase and polarity logic applies rule-based reasoning on top of learned signals. In other words, you combine statistical learning with domain constraints so that the pipeline is not just accurate, but also explainable. Now, above that, we have the agentic layer, which performs risk assessment and packages the results in an interpretable format for the operators. Finally, the system outputs three things together: the predicted PD type, the confidence level, and also the localization. So this diagram communicates our design philosophy clearly: learn from the data, validate with physics, and then reason with the rules and deliver operations carefully to the users. Yeah, next slide. I think from here, my colleague will take over.
Thank you, Humphrey. In this description, I'm going to describe two data sets. One is the acoustic and the electrical data set. The acoustic data set was recorded across 32 array sensor microphone and across 90 locations. Each recording was sampled at 96 kilohertz and it lasted for 50 seconds. And within these 50 seconds, there were 10 repeated sequences of chaps, white Gaussian noise, and partial discharge signals. So the acoustic signal categories were partial discharge, chaps, and white Gaussian noise. In the electrical data set, it contained 250 controlled laboratory partial discharge acquisitions. These were recorded using a high-frequency carrier transformer and equipment that is used to detect partial discharge using the electric signals. So with this, each acquisition was captured across a 35 millisecond time window and sampled at 125. So that the data set contained four discharge types: corona, surface, internal discharge that was divided into the internal solid and the internal liquid. So solid is the insulator and liquid represents the type of insulators. So these are the two selected models these are two models that we selected. One was a spatial temporal graphic neural network that was used to predict location and detect partial discharge. So with this, you had to process the data into graphs. After processing the data into graphs that were they were KNN graphs, which means that with a particular node was connected to the 6 nearest neighbors. So we took the 32 microphones as the different nodes in the graphs. So here we use the communication between microphones in order to detect the whether it's partial discharge or it's not partial discharge, in order to also detect the location. With the location, we used time of arrival, time difference of arrival, in order to get the location. So different sound waves from different locations can reach a particular microphone at different times. So that's what we use in order to find out where a particular signal came from. So with using that, we pass it through attention layers in order to pay attention to the most important features. And then from there, we had two heads: a classifier head that would detect white noise, partial discharge, or chaps, and a localization head that was able to detect where this particular partial discharge is coming from, or a particular signal is coming from. And then here we have a Gaussian process classifier that was used on the electrical data. So here it intakes an electrical partial discharge signal, and then it carries out the processing, extract the features, it scales the features, make sure that they're in the same the inappropriate range, and then it uses the classifier in order to detect whether it's corona, internal, or surface. So from these two models, we're able to train a model. Since the first model lacked a way of classifying the partial discharge, it would just detect that this is partial discharge signal. So what we did was to get the embeddings from the graphical neural networks, and also get the embeddings from the GPC, and then we use the embeddings of the GPC in order to teach the graphical neural network what different types of partial discharge looked like. Since the data, the acoustic partial discharge data was unlabeled, so we had found a way of labeling this data. So what we did was to scale the data to make sure that both the acoustic embeddings and electrical embeddings are all appearing on the same scale. And then we had to use cosine similarity alignment, whereby first of all we had to cluster the electrical embeddings into the different clusters of the different partial discharge types, and then use this alignment in order to find out which embeddings, which acoustic embeddings seemed closer to each of these clusters. With this, we're able to generate pseudo labels that we used in order to classify the different types of partial discharge in this unlabeled city graphical neural network. Of course, this methodology has a few limitations and a few assumptions that we use, but we're going to explain that in the next slide. So the output results for the fusion model, we had the corona. We start with the class 0, which is the corona. With the corona, we had a high precision, the recall, and the F1 score. So you can see these results. These results are relatively okay, except the recall result that dropped to 67%. And if you look at also the questionable results for class 1, the internal class, we had also a result of 44 on the precision aid, which means that the model struggled mainly with identifying the internal discharge. And the best performing class you can see here is the surface discharge class. So it means that we need more work in order to get better results, especially with the corona and internal discharge. So if I had to go to the confusion matrix, you see there's a bit of confusion. I'm to zoom in. There's a bit of confusion between class 1 and class 2, confusion between internal and the corona discharge, whereby you find six mislabeled classes and a little bit of confusion, whereby we found that only one class, one surface discharge class was labeled as corona. But here we see there is a bigger confusion between corona and internal. The same for the normalized confusion matrix. It talks about the same thing. And the class distribution, we see class 1 and class 2. Class 1 especially struggling, whereby we see more classes. There are more false positives, mainly in class 1, whereby you see there are more predictions compared to the true classes. And then in class 0, we see that the true classes are more than the predicted classes. It's only in class 2, which is surface discharge, whereby we see a bit of an equal level of the number of predicted and non-predicted. And so if we were to go to the ROC curves, with the ROC curves, we see that the true positive rate and the false positive, we see that the model relatively performs well and Of course, we see a bit of a hiccup in class 0 and class 1, which is the internal and corona. So you see corona and internal coming up as classes in which we need more improvement compared to the surface discharge class, which was detected well. So the last graph I'm going to talk about, we see the incorrect predictions having a lower confidence compared to the correct predictions, which is some good news for the model, which shows that if it makes an incorrect prediction, there is a lower confidence attached to it. But if the prediction is correct, we see that there are higher confidences, meaning that the model is sure of these predictions, especially the correct ones. We only see a bit of a hiccup whereby we see one bar here. So with the precision and recall, of course, we see class 1 and class 0 struggling, having a bit of a struggle, but class 2 is doing well. So overall, we had an accuracy, a training accuracy of 92 and a test accuracy of 86%, which is expected since this is unseen data and shows that there is still room for improvement. And of course, the data set, we see that we had fewer pseudo labels due to fewer pseudo labels and just 44 in the validation set, which brings in room for more data collection in order to generate a higher quality of the pseudo labels. So here we go to the explainable AI results. The explainable AI results, we see with these graph curves, we see how each class was predicted across the different graphs, how the graphs behaved and when they were predicting these classes. And then if you are to see here in the visualization, you see the space. So if I see class 1 in the validation set, you see that there are only 4 samples. So that can explain why internal was struggling due to a lower count. And then we see more samples of the surface discharge, which shows that indeed the more the number of samples, the better the performance. So the average confidence by prediction, we see for surface discharge having a higher confidence, but there is still a bit of confusion between internal and corona, as I had said before. So the confidence distribution, we see that the surface discharge, so we see that this model in general tends to do well in the surface discharge, but there's a bit of difficulty with the internal and corona discharge, mainly due to the smaller data set and the lack of quality pseudo labels, since we also had a threshold in determining the confidence, in determining which pseudo labels to use by the confidence. So I'll hand over to my colleague Ayan Mustafa to take us to the next section.
Okay, for me, I'm going to take us through the deployment pipeline and the UI basically. So the deployment system is hosted as a web application, mainly on a Hugging Face Docker spaces that we had generated. This was an important design choice because it helped us to provide a reproducible runtime environment, and this makes the model accessible through a browser. So the deployment architecture, first of all, is divided into several main components, which I'm going to talk about them according to the sequence diagram. So the first component is the front end. This allows us to upload our zipped files and also test the system using graph.json input and view the predicted results in a clear format. So basically, the front end is responsible for collecting input, then sending it to the back end and displays the result returned by the two models. So the second component that we used was the Flash backend. The Flash backend acts as the central controller for the deployment. So it checks the input type, decides whether the audio preprocessing route or the graph JSON route should be used. And then it passes this pre-processed data into an inference pipeline. It also helps us to return a final result as a structured JSON response, which it will then send to the front end, and then it will display it to the user. So the system supports two input modes. The first and the main input mode is the acoustic zip upload, and the second input mode is the graph JSON input. So this is mainly used for testing, and it helps us to also debug, which allows direct submission of graph-ready nodes features without uploading the actual audio. The next major component we have is the pre-processing module. So this is very important because the module does not directly take in raw sounds as inputs. Instead, the raw audio must first be converted into numerical graph features. These values. So at the end of the day, it will form for us 8 feature representation, which we got from all the different channels. We also have another supporting component, which is the metadata, CSV. So this file, what it does is that it's used to validate the uploaded audio file names. Then it helps us to recover the original event and information, which we'll also use for testing and carrying out validation. So after pre-processing, the graph builder converts the extracted nodes features into graph features required by the graph neural network. In this system, each acoustic channel becomes a node. So the graph contains 32 nodes and 8 features. Yeah. The graph builder, then this helps us to mainly normalize the node features. Then it helps us to build using the k-nearest neighbor graph, and helps us to compute our the edge attributes. So finally, the inference architecture is divided into 2 stages. The first stage, it's using the STGNN model loaded based on the the PTH model that we generated. This model helps us to predict the broad discharge class and the location. Then the second stage uses the transfer model, which is basically the fusion model. And this model helps us to predict the subtype, which can be corona, internal, or surface. However, the second stage is only shown when the first stage predicts PD. The back end then sends the prediction results back to the front end in JSON format, whereby the front end then finally displays the information. So those are the 2 links that we have. That is our actual demo. Then the second one will help and lead you back to the GitHub repository demo. Finally, next slide, please. For the next slide, in conclusion, our limitations, a spatial temporal graph neural network is used to extract the rich acoustic embeddings, while the pseudo labels are generated by aligning these labels with electrically derived labels from the Gaussian process classifier. This process helps us to address the challenge of limited label acoustic data by leveraging electrical domain knowledge. This framework can be deployed in real-world scenarios, whereby cheap microphones can be used to detect and classify partial discharge rather than expensive electrical equipment. So the limitations we have is pseudo label noise. The second one that we got was imbalanced and small test sets on the acoustic data sets. Then the third one we got was the dependency on feature alignment, quality. Finally, our next steps is to improve on the pseudo label quality, enhance feature representations, and then larger and more diverse datasets will have to be used, then real-time deployment and edge optimization. Then finally, on our final slide, the acknowledgements, those are the IEE datasets that we used, and the science direct publications that we mainly got from the IEE to refer furthermore on the information that we needed. I'll hand over back to Treasure, please.
Thank you so much for listening to our presentation. We are glad to have presented presented our project. Thank you so much.